Hello, everybody. Welcome to our course on AI for Art Observation. This is the first lecture of this course. In this lecture, we'll briefly introduce what this course is all about. What are the main components of the course? Is this a course for art observation, or is this a course for AI? Should we consider it as a theory course or as an application course? So all these questions we will try to answer, and we'll also try to understand art observation a bit. So with this background, let us go forward. And the very first point to note is that the art observation is not just a single discipline. Sensors, algorithms, and applications form pillars of modern art observation. For this particular course, we will consider the differences in the sensors. However, we are not going to the details of understanding or designing sensors as such. So we are going to take the characteristics like what's the spatial resolution, what is the temporal resolution, or what is an active sensor, passive sensors. And with this background knowledge, we are going to jump into the algorithms and applications. They form the focus of this course. The Earth observation domain involves people with background from several different engineering disciplines, such as electrical engineering, computer science, civil engineering, as well as people from science background, such as physics and mathematics. And also at the same time, researchers from non-engineering and non-science background, such as geography. Well, I mean, the other way of calling, of course, geography is a geographical science, so it would probably not be correct to not include geography in science domain. However, often, especially how we see in India, we often treat geography also a part of the non-science stream, right? So that thereby we see that there is a combination really from so many different backgrounds. And also, this is probably not so much common in India, especially not at the bachelor's level. There are like courses at the master's level, most famously from, let's say, IIRS, Dehradun, or even some IITs offer master's courses in remote sensing. However, not so much at the bachelor's level. However, there are other countries, especially I take the example of China, which has taken considerable amount of interest in Earth observation in the last decade. So there, Even there are bachelor level courses on remote sensing or geographical data science. Okay, with this background, also we need to understand that this is not a field restricted only to the researchers. This field attracts researchers, engineers, environmental scientists, and at the same time, the policymakers. So this, of course, also leads us to another discipline which I have omitted in the list above in the second point. So the Earth observation in this field is like also very important for the policymakers, and so the departments or schools, such as I will take example from IIT Delhi itself, the humanities department in IIT Delhi, and also School of Public Policy in IIT Delhi. For them also, Earth observation is a field of interest. So, talking about IIT Delhi itself, I can just say from my memory, and I might be for sure missing one or two departments, but I for sure know researchers from, of course, I would include my own school, School of Artificial Intelligence. Then there is Department of Civil Engineering, also Computer Science, also Electrical Engineering, also Humanities, HSS, and also School of Public Policy. So there are researchers in these particular departments or academic units who work with one or the other form of Earth observation. With this background, let us go ahead and let us try to understand the different types of data acquisition that happen in Earth observation. So remote sensing is the most dominant form and the kind of data acquisition that we will be talking about for most of this course. However, we have to understand that Earth observation not necessarily just involves remote sensing. Proximal and in situ sensing are also part of Earth observation. They often complement remotely sensed data, and at some points, at least in this course, we will talk about fusion of remotely sensed data and other sensors. So, with this, let us also try to understand a bit the variety of remote sensors. It involves passive sensors, active sensors. So we'll talk about what is active sensor later. So it involves, broadly speaking, multispectral sensors, hyperspectral sensors, synthetic aperture radar sensors, LiDAR sensors. In this course, we will talk quite a lot about applications with respect to multispectral images, application with respect to hyperspectral images, application with respect to synthetic aperture radar images. So, a lot of discussion with respect to the algorithm, where naturally the examples that we'll take are with respect to multispectral images. However, from time to time, we'll keep taking examples with respect to the other two sensors that I mentioned. And most importantly, 2 weeks, that is 1 week each, is reserved for hyperspectral, and SAR. However, here let me also emphasize that here we are just talking about this variety of sensors. However, within each sensors itself, there can be significant variation of data, significant variation of the sensor characteristics, and accordingly, like the data that we acquire can vary significantly. So, one variation that comes in the data is also from the platform for data acquisition, and this variation can come in the form of satellite, aerial platforms, or unmanned aerial vehicles. Here again, we have to understand that when we say that we are talking about the satellite images, they themselves are not just a single group. There can be significant variation with respect to whether we are talking about geostationary satellite or polar satellite. So we will talk a bit about these variations later, not in today's lecture. However, let us go ahead with this understanding that with these particular platforms, that whether we are talking about satellite platform or aerial platform or UAV, and within them the differences, they cause significant variation in the remotely sensed images, and this in turn impact how we design the algorithms for them. In addition to the different types of remotely sensed images that we just briefly mentioned, it's also important to understand that the remote sensing or the earth observation analysis often involve ancillary data. So this briefly I had mentioned before when I was talking about the proximal or in situ sensors, right? So this ancillary data may come in form of existing old maps, street view images, weather data, proximal and in situ sensors. So these all like how to fuse these street view images with the satellite images. These all discussions will come at some point in this course, how weather data is fused with the satellite images. And it's also possible, of course, that weather data, when we're just saying like, okay, the weather data, this always doesn't need to be from some proximal or in situ sensor. This is often also actually based on satellite data. Okay, so there, let us slowly start talking a bit about the algorithmic challenges that we face when working with Earth observation. One challenge is with respect to the significant variation in the spatial resolution. In this domain, we work with images with as high resolution as 5 centimeter per pixel or 10 centimeter per pixel to as coarse as even kilometer per pixel. And accordingly, of course, the task that we are addressing is significantly varies. When we are talking about few centimeter per pixel, think about even a 224 cross 224 image. This is not that geographically large, right? So maybe we are Like maybe there is just a building there is one road there, and maybe we are happy with assigning just one label to the entity image. Whereas when the resolution is that coarse as few hundred meters per pixel, probably we will rather like to go for a label per pixel, or even we'll try to understand like, okay, what all are there in a single pixel, right? Because in such case, a pixel will not just have one object. Often there will be multiple objects, content within a single pixel. Also, with the variation in spatial resolution, it is important to understand that there is significant variation in the region of interest that we would be analyzing. We can be analyzing just few hundred meters into few hundred meters, whereas we could be also analyzing hundreds of kilometers into hundreds of kilometers. So this is aspect that I just discussed, that for a given ROI, you might be interested in producing one output or producing a dense output. The algorithmic challenge also involves how to blend information from different sensors. So if we are working with different sensors with different spatial resolution, sometimes it's beneficial to fuse the information from them, and image fusion is indeed one of the main themes in this course. So the challenge lies in how to indeed effectively fuse the information from these sensors, which show such strong disparity in spatial resolution. Till now, the previous two challenges that we discussed, we were talking about mainly the limitations or the challenges from the point of view of spatial resolution or spatial analysis. However, the most important aspect of art observation comes from temporal analysis. We are often interested in understanding how our environment, how our earth is evolving. And there again, there is a strong disparity in the temporal resolution offered by different sensors. So here, the first point to note, which I have seen like many people working first time with art observation, they don't automatically realize that it's not the case that you are getting constant coverage of an area from a satellite. In most cases, a satellite would be coming back to your particular ROI. Let's say we are in Delhi, and the satellite would be coming back to Delhi only after a few days. Depends again on like, okay, what type of satellite and all we are talking about. Most of the time it's in days and like can be tens of days also. And this particular gap is also not uniform from one sensor to another sensor. And there, let's say we are interested to analyze more than one images because we want to detect changes that are occurring in our surrounding, or we want to even go beyond two images. We want to do a time series analysis that involves n images. Here we would need to redesign our algorithms that we would have otherwise designed in the context of monotemporal images. Also, at the same time, the change detection problem, the time series analysis problem often involves other complexities such as how to work with images from different sensors. The first question that one would probably ask is that why are we even talking about different sensors? And that answer already we kind of answered in the last slide, that over a particular area from a particular sensor we generally don't have constant or even everyday coverage, which means if we want more frequent coverage we would probably like to combine images from different sensors in our time series. So this is aspect that I just discussed. Also, another important aspect in working with Earth observation is working under different annotation settings. Depending on what is our exact problem statement that we are working on, it might be the case that we are working with some amount of label data, which we know for sure that this label data has been labeled properly. However, in practical applications, most of the time, the scenario is a bit different. We rather work with some amount of label data where there is a chance of incorrect label. So we are not saying all the 100% data is incorrectly labeled. That would mean, of course, the data is no good. We are rather saying, let's say, like some percentage of the data, moderate percentage, like let's say 5%, or even 10% of data could be incorrectly labeled. We can also, and this is also very practical scenario, work under the setting that no data is labeled, and this leads us to self-supervised learning, which is also very strongly adopted later when we talk about foundation models towards the end of this course. We have to also consider the huge application varieties that is offered in Earth observation. Earth observation is indeed part of our daily life. Many of us probably live in cities. So let us start thinking about this variation from the cities itself. Let's say we are interested to answer this question: how good is our city doing in the terms of urban green? One way, of course, could be that the municipality actually sends surveillance van to all the places around the city and do a survey. I mean, just think the amount of time that this process would need. I'm not talking in the terms of the cost, of course, cost is also another thing. Whereas now think the same thing to be done from some UAV, let's say. I'm not yet to the satellites. The process becomes significantly faster, where the UAV probably just goes around the city. Whereas still one has to understand that operating UAV still is a process which would need some amount of coordination, and which tomorrow if you need to do it needs kind of repeat. Whereas with the satellites, this amount of repeat effort, of course, sending satellite for the first time is an effort. And I'm not saying that there is no effort in maintenance. There are efforts, but otherwise the result that you get out of the satellites, that would be kind of recurring. So with the satellites, if you want this particular answer on monthly basis, you can get it quite conveniently. Similarly, think another problem statement. Informal settlements are indeed pretty much part of urban life. As long as cities will exist and as long as they have existed, there have been migrant workers to the cities and thus there have been informal settlements. However, it's also important for a healthy city that the informal settlements, the ratio of them, they stay limited within, I'm not saying a particular number that's beyond my capacity, rather more a policy study question. But let's say for this reason, the city authority wants statistics of the informal settlement. And again, one of the most convenient way of answering this is from the analysis of the satellite images. However, now just think a bit with respect to what we discussed in the last application. There, we were just interested to have an understanding of the urban green, and the assumption is that I'm not talking that okay, we also want a clustering or classification of the different kinds of trees or vegetation. that would be a different problem. And we just want statistics of the urban green. And compared to that, let's say we rather want detection of these informal settlements. Which one do you think would need higher spatial resolution images? Think a bit about this aspect, and we would carry forward our discussion in the next lecture. Thank you.